Rehash a couple things with surface area prisms, and then talk about how prisms morph into cylinders and how that morphing process occurs and what it means for us in regards to some formulas. Then do some cylinder problems, and then at that time it should be about 3:10. Okay, so that's the plan. I have opened up the. I wanted to do this on Friday, but I started to think a lot of people were involved in that musical and did not probably want to spend time this weekend working on the take-home test. Okay, therefore they'd be out 2 days, 3 days maybe, in regards to everybody else that was able to use this weekend for the take-home test. So I am assigning that today at 3:15. It's already scheduled to just turn on at that point, and then it will be due next Monday at midnight. Okay, so that gives you next weekend to work on it if it takes you that long. My suggestion, we listening? Don't wait till Sunday to work on it, because if your Wi-Fi doesn't work on Sunday, there's a guy with 2 thumbs that doesn't care.
Is there, is it 11, is it just 10 or 11 also?
Just chapter 10. Okay.
Do at 12 o'clock, right?
Due at 11:59 p.m. on Monday evening. Okay. Did I say Sunday? I meant Monday. Monday, 11:59 p.m. There's some stuff in your emails. I just sent you out, like, if you want to come and go from that, how to do that. All right, getting into this example. We're going to find surface area. Surface area for any prism is found by taking this formula and finding those key components for that particular prism. This is a formula that kind of adjusts based on what your bases are. Does that make sense? Whenever I deal with a prism, lateral area is just going to be a sum of a bunch of rectangles. Sometimes those rectangles will be congruent, sometimes they will not be. Okay? But if it's an octagon, it's 8 rectangles. If it was a decagon, it'd be 10 rectangles. If it's a hexagon, it's 6 rectangles. That makes sense? So that LA changes the amount of rectangles per prism. The 2B, obviously the capital B, represents the area of the base. That is the thing that also transforms from a triangular prism to a rectangular prism to a hexagonal prism. The base changes shapes. Therefore, that formula, that capital B, might be 1/2 BH. It might be BH. It might be 1/2 HB1 plus B2. It might be 1/2 D1 D2. Okay? It might be any one of those two-dimensional shapes that we talked about last chapter. Okay? So that formula allows for that kind of adjustment. Okay? In regards to doing this, first thing is you're going to find lateral area. Lateral area is always perimeter of the base times h. Okay? Now, as you're working through these problems, h is going to reappear multiple times. Okay? There's a chance that it might show up with the capital B formula. It doesn't in this one, but it could. It does in others. Okay? Right there, that h is the altitude of the prism. The h that you would use in any capital B formula, 1/2 BH, 1/2 HB1 plus B2, that kind of thing. Any one of those formulas, the h of the prism and the h of the base are never the same number. Okay? If you view it that way, you're going to obviously make mistakes. This is the we refer to as lateral area of the prism. So this is the altitude of the prism, or h of the prism. My fear is that we would be on a question like this, and I think we did this one on Friday. Okay? If my formula is LA equals pH, and B here is 1/2 BH, because it's a triangle, right? I want to make sure that we realize that this H is maybe that 4, or it could be a 3, and that this H is the 6. Does that make sense? Okay? Notice they're not the same thing. Okay? Now, this could be a 6 at some point, and this could be a 6. But where we pull them off of the picture or off of the figure, they're not being pulled from the same dimension. Does that make sense? They're not the same segment. Those are things to think about as you work through these problems. Okay? Now, in regards to this question, the base is a regular octagon, so that formula is 1/2 A times capital P. Okay, so we got that, we set that stuff up, and now it's just mainly figuring out what these components are. What is the perimeter of your base? 40. Remember, the base is, if there are shapes that are non-rectangular that show up, those are your bases. So those octagons are non-rectangular, so those are my bases. So the perimeter of that base, 5 times 8 is 40. What is the altitude? So this is the H of the prism, lateral area of the prism, so it's H of the prism. What is the altitude of that prism? 22. Multiply that together, 880. Okay? Is that doable? All right. Now working through the other part, working through capital B, what's nice about this is that you already know one of these values. Which one of these values do you know, A or P? P. P is 40, right? Okay. Now, here's where people kind of go astray with these types of questions, is because of our familiarity with Chapter 10 and our retention of information in Chapter 10, we forget to find how to find A. Remember, we take our octagon, we go from the center of that octagon, we draw a perpendicular down to a side, and that's our apothem, right? That apothem and your radius create that angle, which is always found by 360 divided by 2n. N being 8 in this case, so I get that, which ends up being 22.5 degrees. Is that okay with everybody? 16 is your 2 times n. So n being the number of sides you have, so we've got 8 sides in an octagon, and we just double it. Because the dividing by 8 is actually going to find me the central angle here, and then we want to cut that in half to get just that one. So that's 22.5. Now what is this distance here? In this case, it's going to be 2.5. Okay? And right now, guys, I know I've been on a kick of doing things with exact values. With this type of stuff, usually they're going to ask you round to a decimal place, that sort of thing. So I'm not concerned about writing that's 5/2 or anything like that at the moment. Which trig ratio would you use if this is opposite and that's adjacent? Tangent. So say tangent of my angle is equal to 2.5 divided by A. A is then 2.5 divided by tangent of 22.5. All right, so then we are going to grab our calculator. Maybe. All right, so the area of our base was 1/2. Like somebody in school actually thinks that's appropriate. So 1/2. Now my apothem was 2.5 divided by tangent of 22.5. And now my perimeter is 40, correct? Now that's just one B, correct? How many B's do you need for surface area? You need 2 of them, right? So if I put a 2 out in front of that, what's that going to do with the 1/2? Cancel them out. So this number right there is 2B, okay? So I need to add my lateral area to that. My lateral area was 880. And I think I put a subscript, there we go. So 1,121.42 square, I don't know what units we were talking about there, but square units. Is it okay? Huh? Yeah, I mean, they'll tell you to round to whatever decimal place in Excel. Going through Just practice questions, just trying to preparing for some stuff that I'm going to give you guys here in the near future with the end of course exam. There are a lot of questions in the end of course exam that actually ask you to round to a particular decimal place, but there is still a handful that ask you to write them simplified. Okay, we're using radicals and that sort of thing. But there's more just looking at the practice. Now that the test has been out for several years, we have more practice resources than what we did when it first came out. Just kind of looking at that stuff, there's a lot more rounding than I remember. Okay, so that is a nice thing, I think, for you guys. Is that something we can do? Okay. Now, I want to talk about how there are times that you might have to adjust your formulas. Okay? Sometimes, and we're not going to do this example, but there's going to be times where maybe there's a story to the problem, and they say maybe this octagonal prism is like a box, a container for something. Okay? And the top is made out of plastic, and the rest of it's made out of cardboard. And we want to know how much cardboard we need to make that prism. So we have to adjust our LA plus 2B to look like LA plus 1B. Does that make sense? Okay. So you can, based on the contextual aspects of the story problem, you may have to or can change your formulas to address those. Okay. So just be on the lookout for that, especially with story problems. You've seen maybe if you've done your homework or looked at it, there are questions towards the end of it that look like this. Okay. That is an irregular, what we call an irregular composite shape. Okay. Composite meaning multiple things put together, right? Hopefully you see there's a prism there and two separate half cylinders. Obviously that doesn't have a traditional, this is the formula for that shape, because you'll probably never see that shape again in your life. Okay, so why need a formula for it, right? So we'll have to take our formulas that we know, maybe 2 or 3 of them, and kind of amend them, kind of adjust them, so we can find that unique surface area for that shape. Okay? Same thing happens maybe in this one. Okay? That's a unique shape that you're probably not going to see very often. So why have a formula for it? You can use your current formulas with additive ideas, subtractive ideas, and adjust them to address what that area would be. Is that right? We'll do that a lot with surface, or not surface area, volume eventually. Okay. So that gets us into talking about cylinders. Okay, so we did a prism question, octagonal prism. Now my hopes are you can see that if we look at that octagonal prism, start putting more sides on that thing. Start making that octagon go to a decagon, go to a dodecagon, go to a 20gon, and start visualizing what that would look like. And I think maybe I've even got something here for us, but I do. I did this last period. Give me a second. It might take a minute to load. So if I look at just the blue prism, triangular prism, right? Okay. Start adding sides to that thing, and now I get that rectangular prism, pentagonal, hexagonal, heptagonal, octagonal, nonagonal, decagonal, or decagonal, however you want to say it. Oh. Okay. So that's a prism with 10 sides, right? Okay. Now, as I look at, so this is the base, right? As I add sides to that base, but I confine the sizes, so it's not growing, right? It's not getting overly large. Each of these side lengths between 2 consecutive vertices over here is getting smaller and smaller when I go from 3 sides to 4 to 5. Okay? What is eventually going to happen between these distances, or in regards to these distances? They're going to be very, very small. Okay, right now, they're that size at n being 20. But if n was out to infinity, that size would be infinitesimally small. Does that make sense? Meaning that those points would almost be on top of each other. Meaning that those surfaces, so look over here then. So the distance between these 2 successive points is providing me one of these rectangles, right? Well, eventually when this is out to infinity and that distance is infinitesimally small, okay, that rectangle over here is actually going to just be almost a straight line. That's it. Does that make sense? The width is going to be 0.000, an infinite number of zeros and a 1. Well, if you got a bunch of those around there, doesn't that shape start to look very cylindrical? Does that make sense? Okay. So here's the idea. Let's say that so the idea is that at infinity, an infinite number of kind of sides, or an n goes to infinity, that thing has become a cylinder. But at infinity minus 1, it's still a prism. Does that make sense? Let's say infinity is the number 20, and then n minus 1, or infinity minus 1 would be 19, right? Let's say at this juncture, right there, that shape is a prism. Let's say when I go to 20, right now, it is a cylinder. Was there much of a change between those two shapes from 19 sides to 20 sides? So is there going to be a huge jump in regards to their surface areas? No. So when a prism at some juncture is a prism, but the next you add one more side to it and it becomes a cylinder, there can't be a huge jump in surface areas. Does that make sense? And if we understand that concept, that's a calculus concept with using limits and that type of stuff that you guys will maybe encounter at some point in your life. That allows us to make the conclusion that the surface area formula for a cylinder is no different than the surface area formula for a prism. They are the same. LA plus 2B. Okay? Now, for a prism, LA could be 10 rectangles, it could be 12 rectangles, it could be 20 rectangles, it could be 1,000 rectangles. Okay? For a cylinder, okay, and this is why I was hoping my web page would open. It's not. These aren't. I don't know why these don't work. You've probably seen this, and I'll see if I can get it working to show you tomorrow. This animation that actually, if you look back here, we'll use this. So let's say if this shape is now. I know it's oblong because the poster's been scrunched up for about 3 years. But let's assume that that's a cylinder. You want this one? I'm done with it. Show Thomas.
No, I have like 4 of those.
Okay. It's actually the autograph plan. So we've got that as a cylinder, right? Assume that that's a perfect circle. Okay. What would you call this distance here for this cylinder? Circumference. Now, if I cut down the side of the cylinder and unfold it, that circumference just became the what of that rectangle? It became the length, right? And this distance, the altitude of my cylinder, became the height of that rectangle, right? Does that make sense to everybody? So what's the formula for circumference? Okay, yeah, you're right. Got it all backwards, but 2 pi r, right? Okay, so 2 pi r. So when I pull this apart, that's what the length of that rectangle is, right? 2 pi r. Okay. So looking at this, that's what they're trying to work through here in these couple pictures. You've got your normal cylinder. You're going to cut that cylinder right there and start to unravel it. Well, when I start unraveling it, that distance right there, that blue distance, was glued to or attached to that circle. When I lay it all flat, that distance right there is 2 pi r. This distance here is h. How do I find the area then of that rectangle? Base times height, right? 2 pi r times h. And that is your lateral area. Is that okay? So 2 pi r h. Now for a prism, lateral area is ph, right? P stands for perimeter. What is 2 pi r for a circle? Circumference, which is analogous to the perimeter of a circle, right? Okay, so it's still pH, okay, as our lateral area, but P is now just the circumference. Now, B, what is that shape right there for B? Yeah, it's pi r squared, circle. So we have 2 pi r squared, okay? This formula is not wrong. If you want to go LA plus 2B for a cylinder, it's not wrong. But generally speaking, they're going to give you 2 pi r h plus 2 pi r squared on a reference sheet. And the reason for that is because cylinder 1 compared to cylinder 2 compared to cylinder 3, are always going to have the same components. The lateral area is going to be a rectangle, and the bases are always going to be circles. But prism 1 to prism 2 to prism 3, bases might be triangle, hexagon, square. And now that formula has to adjust and change, right? But for a cylinder, the formula doesn't adjust based off cylinder 1, cylinder 2, cylinder 3. Okay, they're all the same. So 2 pi RH plus 2 pi R squared. Is that something we can do? Okay, so we see some examples. I'll run you through some, or at least one kind of elementary type example, and then see some more complex ones. So here, I think it's a good idea. A lot of times they might not give you a picture. Draw a picture. So we've got a cylinder. And they ask us, okay, it says the radius is 4 inches. And the height is 6 inches. So if I want total surface area, 2 pi RH plus 2 pi R squared. What is R? The radius, which was 4. What's H? 6. What's 4 squared? 16. What's 2 times 4 times 6? 48. So we got 48 pi. What's 2 times 16? 32. So we got 32 pi. 80 pi. Okay? That's hopefully something that maybe you addressed in previous courses. 7th grade, 8th grade, how to do that. And of course, exam not going to ask that. And of course, exam is going to do a couple different types of things. Maybe the end of course exam says, we're going to take that, okay, and we're going to drill out a circle in the middle or a cylinder in the middle. So maybe we got a roll of toilet paper now, right? And we want to know what is the surface area of that roll. Okay? So now you've got to kind of adjust things and realize that there's some additive processes going on when we do that. Okay? And there's some subtractive processes going on when we do that. And we'll go through a couple examples like that here in a moment. If you've gone to the end of your homework assignment, you've seen maybe pictures like this. Okay, this tends to be one of the harder types of questions that we deal with in that assignment. Okay, first thing I need you guys to understand, not a regular shape, right? Not something that you're going to see over and over and over again. This might be the last time you see this picture in your life. Okay, but we want to find the surface area. Surface area is the idea of painting something, right? Let's say I want to paint this thing. Would you guys agree? So what they're showing me right there is that that's a diameter of this half circle. Okay? Would you agree then that that is a cylinder? But how much of a cylinder? Half. Okay? So you can find the full surface area of a cylinder and then divide by 2. Or if you just want to say the surface area of that purple one is pi RH plus pi R squared, did that take a 2 out of everything? Yeah. Okay. Or divide everything by 2. So you'll find that surface area of that cylinder, or that half cylinder. The radius is going to be what for that purple cylinder? Be 7, right? What's the H going to be for that cylinder? It'd be 8, correct? Okay. So you go through, you run through that process. Find that surface area. Is this another cylinder right here? It's another half one, right? Okay. What's the radius of that? 7. What is the height? 4. You can find, you go run through that and find that surface area divided by 2 because it's not a full cylinder, right? Okay. What does that turn this shape into right here? A rectangle. Can you find that area? Okay, you find that area in, that's 32, right? Is that surface going to be repeated back there? So you got to add 32 in twice, correct? Is everybody okay with that? Now, have we talked about that surface yet? No. Okay. What's that surface's height? 4. What is this distance? 14. Because it's the same as this one, right? Okay, so it's 14. So 4 times 14. Can I find that area? Yes. Now, is that area, so that area is also going to be right here. It's going to be that rectangle that is on the inside. Can you reach in and touch that? So do I add that area in? No. Okay. But there is an area yet that we have not talked about, which would be this bottom one. It'd be that area right there. That'd be 8 by what? 8 by 14. We can find that area, right? So in this one, you're going to find 2 half-cylinder areas, and then you're going to basically go around and find 4 rectangles that you can actually touch. And that's the hard part about some of these 3-dimensional shapes, because they're being rendered on 2-dimensional surfaces, paper, computer screen, that kind of thing. It's hard to interpret what things you can touch. Okay, so you got to kind of have that 3-dimensional shape in your mind's eye and be able to rotate it and that kind of thing to see, you know, if I wanted to paint this, what parts can I touch to paint? All right, so that'll be a task in your homework, but that gives you kind of the kind of rough approach, rough steps to being able to do that. Okay, now I want to spend the rest of the time doing this one. Okay, thank you. The cylinder there is a bead, obviously not a very big bead, but it needs to be painted. We want to paint the inside, we want to paint the outside. Okay, inside and outside. So you want to dip it in, and that's fine. But when I dip it in there, that paint is still going to cling to it, right? So let's say I want to make 1,000,000 of these things. I still need to order the right amount of paint. I still need to know the surface area that paint's going to cling to, no matter what technique I'm going to use to paint it. Okay. Now here's the thing. Why would I want to do this? Now we're doing it for a bead. Let's say that I am a manufacturer of something. Now I know like Pepsi doesn't have, obviously they're not painting the inside of their can, but let's say that I'm for some reason manufacturing something that needs something printed on it, okay? Like a Pepsi can or a Mountain Dew can or something like that, right? Now would Pepsi be real happy with the people in the painting department for their cans if they had to stop production and lose all the money on sales if they had to stop and wait for paint to be delivered? They ran out of paint. Do you think P&G would be happy if they had to shut a line down if they ran out of material to box Tide Pods or something like that? So there are groups. Now they might not. So P&G, Ford, Chrysler, Honda. I mean those are national, sometimes worldwide corporations. So they might not have an analytical group or a math group kind of on the Lima campus at Ford. Yeah, I bet they do at least have at least a person. But there are, in mathematics, and that if you take a math major, these are options for jobs. There are people that sit and crunch numbers to allow CEOs, people that make decisions, to make good decisions. Because you don't want to just order a bunch of paint, right? Because you don't know how much you're going to need. So this is kind of preliminary stuff that you would go through to say, okay, we're going to make X amount of beads. It takes this amount of paint to cover that surface area of that bead. This is what we project the amount of paint that we need. Okay? So those are all things that kind of go into the manufacturing process before manufacturing takes place. Okay? Now, the fact that this is a bead is, it doesn't have to be a bead. It could be any good that we're trying to manufacture and distribute. Okay? So this gives me an idea of trying to find surface area. I need to paint the whole thing, so I need to find surface area. Understand that this is a hole right here. Okay? We chiseled out the inside, or drilled out the inside so that I can string a string through there, right? If we go to this picture here, okay, kind of makes it a little bit easier to kind of see what we're doing here. Notice that blue one would be a hole, right? Does that make sense? We cut it out, we drill all the way through, and we kind of punch out this end as well. Okay, so you put a string through there. Okay? If I wanted to find the surface area, first thing that I think would be important to do is to eliminate the idea that this thing has a hole in it. Let's just look at that. Does that make sense? Okay, can you find that thing's surface area? Yeah, so let's go back to this screen where we've got the information. If I want to find the surface area of the cylinder, that's 2 pi RH plus 2 pi r squared, right? What is r going to be here? Okay, so I'm going to write it this way, 9/2. And what is h? 20, right? Okay, then we're going to add to it 2 pi r squared. What's 9 squared? 81. What's 2 squared? 4. So now the reason I like to write this as 9/2 is because I didn't know what 4.5 squared is going to look like. But I do know what 9/2 squared is going to look like, so that's one benefit. Another benefit, this happens a lot, is that 2 and that 2 cancel out, right? What's 9 times 20? 180. So we got 180 pi. Now over here, there is still cancellation. It's not as nice, but it's still cancellation. And I get 81 pi over 2. If I want to add those together, what do I need? Common denominator. So I'll multiply this one by 2 over 2. So what is 180 times 2? 360. So we have 360 pi plus 81 pi. What's that give me? 441 pi, and it'll be over 2. So that is the area of the cylinder. Is that okay? All right. So it's the area of the cylinder. I knew this was going to happen. We're lagging. Can't do that. All right, so I don't think that GeoGebra is going to be able to kind of pop back open here. But if that's, oh, maybe. I'm actually going to try to close it. When the, I don't know if we've experienced this in this class, but when the 3D stuff is running on GeoGebra, it takes a lot of computer power, RAM, and so does the recording. So that's why it shuts down. Okay, so let's kind of go back to this picture, and we'll do it up here. So you've got this cylinder, and we said that was 441 pi over 2, right? There's a square here that we're going to chisel out. We're going to cut it away. So if in the painting process, is that blue square up there on the whiteboard, is that going to be painted surface? No. No, it's not going to exist, right? So how big is that area? It's 9. It's 3 by 3. So if it's not going to exist, do I need to add it in to my, or should it be added into my area?
Might as well.
I need to subtract it. I need to get 9 out of there. Okay? Now, that hole goes all the way through to the other side, right? Okay, so I remove 9 here. Is that a hole? So I should do what? Remove 18 instead. Okay? Now, when I do that, you cut through this. You create a what? A tunnel, and that tunnel, you can paint the walls, right? Okay, so it's a prism. And the walls of that prism that you're going to paint would be the what of the prism? It'd be the side, so it'd be the lateral area, right?
Why would you paint the inside of a bead?
Why not?
You're on a stream. No one's gonna look inside on your.
Maybe I'm trying to make it waterproof.
How did you get 180 plus 81?
I multiply that by 2. So that's 360 right here. So now I need to find that lateral area of ultimately that prism is going to look kind of like that, right? That's one wall. This would be the ceiling, and we do the bottom, the floor, and we do the other wall, right? So find that the lateral area is P times H. The perimeter of that square is 12. The height of that prism is 20. So that's additive area that I need to paint. Okay? So I can write that as 441 pi over 2 plus 222. And that will give me that total area. Does that make sense? Okay. Now, the whole idea, why would I paint the inside of that bead, all that kind of those types of questions, it's just a problem that gets you to use these different approaches, right? To amend your formula so that you can address the situation. There are logical reasons why, in special cases, why that would be important to do. Okay? And you can take what you learn here and apply it in maybe more realistic, more authentic types of questions. Okay? No new homework. 10 or 11-2 is still open until Wednesday. Make sure that you look at that. If you have any questions over, we can ask those and address those tomorrow. And that test is open now, so you can start that this evening as well.